You're a software engineer, right? Maybe you're doing DevOps or SRE, platform engineering or infrastructure work. You're using large language models, or at least you should be. But which ones? How do you know which model to pick? Now, I was in the same situation. I made choices based on gut feelings or benchmark scores that didn't mean anything in production or marketing claims. I thought that I should change that. So I ran 10 models from Google, Anthropic, OpenAI, XAI, DeepSeek, and Mistral through real agent workflows, Kubernetes operations, cluster analysis, policy generation, systematic troubleshooting, production scenarios with actual timeout constraints. And the results were shocking, at least when compared to what benchmarks and marketing promised. 70% of models couldn't finish their work in reasonable time. A model that cost $120 per million output tokens failed more evaluations than it passed. Premium reasoning models timed out on tasks that cheaper models handled easily. Models everyone's talking about couldn't deliver reliable results. And the cheapest model? It delivered better value than options costing 20 times more. By the end of this video, you will know exactly which models actually work for engineering and operations tasks. Which ones are unreliable, which ones burn your money without delivering results, and which ones can't do what they're supposed to do. In this video, I'm comparing large language models, or LLMs, from Google, Anthropic, OpenAI, XAI, DeepSeek, and Mistral. Some of these companies have multiple models in the comparison, so we'll see how different versions stack up against each other. Now, you might be wondering, hey, why am I creating my own comparison instead of just relying on existing benchmarks? The primary reason is simple. I need to know which models work best for the agents I am building. But there is a secondary reason that's probably more important. I want to truly know which model performs better and under which conditions. This cannot be based on my feelings or personal experience. It needs to be based on data. We are engineers, damn it. We're supposed to make decisions based on data, not how we feel. Well, some of us at least. I also don't trust the standard benchmarks because models are often trained on them to game the results. So, how am I doing this? I have a set of tests that validate whether my agents work correctly. I run those same tests for each of the models. Since these are actual tests, I know whether the output is acceptable or not. When tests fail, I analyze what's wrong and add that information to the datasets. Those datasets include duration, input and output tokens used, the prompts themselves, error responses, pass and fail statuses, and so on and so forth. All that data is then injected into prompts that run the actual evaluations and provide scoring. Now, this approach is slightly different from standard AI evaluations. Most evals have to figure out both whether something worked and how well it worked. Mine doesn't. The functional tests already determined if the output is acceptable. The evals are scoring how well it worked with full context about what passed or failed and why. It's a more grounded approach because the scoring is based on real-world agent performance, not trying to guess if something is correct. Now, all the models were compared using the same agent based on the Vercel, something like that, SDK. That means I'm ignoring the differences in performance you would get from specific agents like Cloud Code. Those differences can be huge, but that's not what I'm testing here though. This comparison is about the models themselves. Now, as for what I'm actually testing, well, I'm not measuring code generation directly since that's more subjective. Instead, all the tests are based on Kubernetes, which is well understood by all these models. I expect the results would be similar for any type of development tasks, but these specific results are fine-tuned for DevOps or Ops and SRE type of work. Now, let's break down exactly what criteria I used to evaluate those models and what scenarios they were tested against. Now, I believe understanding the criteria and scenarios is important for making sense of the results. But, hey, if you're anxious to see which models won and lost, feel free to skip ahead to the next section with the results. I won't be offended. I promise. So, I evaluated these 10 models across 5 key dimensions. First is overall performance. Basically, quality scores measuring how well each model handles different types of agent instructions. Second is reliability. Can the model actually complete evaluation sessions without crapping out? This is measured by participation rate and completion success. Third is consistency. How predictable is the model's performance across different tools? You do not want a model that excels in one area but completely fails in another. Fourth is cost performance value. Your quality score relative to pricing per million tokens. Raw performance doesn't mean much if it costs 50 times more than alternatives. And the last one is context window efficiency. How well models handle large context loads. Some scenarios send over 200,000 tokens to the models. Having a massive context window doesn't guarantee good performance if the model cannot actually use it effectively. Now, timeout constraints are critical here. If a model cannot deliver results in reasonable time, it's not useful in production. Real-world agent workflows have time budgets, like 5 minutes for quick pattern creation, 45 minutes for comprehensive cluster analysis. When I say an evaluation failed, I mean the timeout was exceeded. It isn't about models working indefinitely. It's about delivering what we need in reasonable periods of time. So let's look at the 5 evaluation scenarios. Each one tests different aspects of what makes AI agents actually useful in production environments. First is capability analysis. This is basically an endurance test that puts model through about 100 consecutive AI interactions over a 45-minute period. The goal is to discover and analyze every single Kubernetes resource in the cluster. What makes this challenging is maintaining quality throughout those marathon sessions while demonstrating deep Kubernetes knowledge for each resource type. The question we're asking is, can the model sustain performance without degrading over extended workflows? This matters because in production, you need models that don't get sloppy or confused after dozens of interactions. Interestingly, 70% of the models we tested completely failed at this. Completely. Second is pattern recognition. This evaluates how well models handle multi-step interactive workflows within tight 5-minute timeout. The workflow goes something like this. Expand trigger keywords into comprehensive lists, abstract those specific requirements into reusable organizational patterns, and create templates that get stored in a vector database. Think of it as capturing your team's development best practices so they can be automatically applied to future deployments. The challenge here is speed combined with abstraction, transforming specific requirements into general patterns quickly. What we're really testing is how well the model handles rapid, interactive refinement workflows. This matters because in production, you often need quick answers for pattern matching, not deep philosophical analysis. The third is policy compliance. This tests whether models can perform schema-to-schema analysis of cluster resources within a 15 minutes timeout. The tasks involve expanding policy triggers into comprehensive resource categories and generating complete, syntactically correct Kyverno policies with cell validation expressions. This is about proactive governance, integrating security and compliance requirements directly into AI recommendations rather than blocking manifests after they're created. The challenge is in time pressure. Comprehensive schema analysis cannot be rushed, but you also cannot take forever. The question is, can the model balance depth of analysis with time constraints? 30% of models completely failed this scenario because they didn't have large enough context windows to handle the schema complexity. Fourth is recommendations. This is manifest generation under extreme context pressure within a 20-minute timeout. The context load here is brutal. Up to 50 large Kubernetes resource schemas totaling over 100 or 200,000 tokens. The process involves transforming user intent into production-ready YAML manifests through targeted clarification questions. What makes this different from generic deployment tutorials is that it needs to understand your specific cluster's capabilities, your organization's patterns, and your governance policies. The challenge is processing this massive schema context while still being accurate. The question we're testing is, hey, how efficiently does the model actually utilize context windows for complex generation? This is where we learned that having a massive context window doesn't mean the model can use it effectively. 50% of models failed at manifest generation within the timeout constraints. Fifth, and finally, is remediation. This one is different from the previous scenarios. The earlier four were one-shot interactions. Hey, send a prompt, get a response. Remediation runs as an investigation loop. The model receives the issue description along with a list of tools it can use. It then decides which kube control commands to run to gather data. The agent executes those commands and adds the output back into the context. The model analyzes the new information and decides whether to request more tool executions or conclude with, hey, here's the problem and here's how to solve it. The model in this scenario is completely free in how it investigates. It could decide it has enough information without executing any tools at all, or it could loop up to 30 iterations gathering more and more data. In practice, successful investigations typically run 5 to 8 cycles, all within timeout constraints for that specific scenario. What makes this challenging is that the model must conduct intelligent, systematic investigation. Kubernetes failures present symptoms, not causes. For example, a pod that will not start might actually be failing because of a missing persistent volume claim or a network policy blocking traffic. The model needs to decide which kube control commands to run next based on what it learned from previous commands, to maintain investigation context throughout all those iterations, to understand cross-resource dependencies, and know when it has enough information to provide the actual root cause and remediation steps with proper risk assessment. The performance variance here was extreme. We saw a 40 times difference between the fastest and the slowest models, ranging from 2.5 seconds to over 22 minutes for the same investigation. So those are 5 scenarios testing different aspects of what makes AI agents useful in production: endurance, speed, attention to detail, context handling, and systematic investigation. Now, let's see how these 10 models actually perform. Let's start with what honestly shocked me the most. 7 out of 10 models, that's 70%, couldn't complete the capability analysis within 45 minutes. They just ran out of time trying to work through those 100 consecutive interactions. Half of the models exceeded timeout constraints for manifest generation. 3 out of 10 failed at policy compliance because they couldn't finish the work within the 15 minutes window. Now, this is important to understand. When I say a model failed, I don't mean it crashed or threw errors. These are timeout failures. The models were still working, still trying to complete the task, but they couldn't deliver results within reasonable production timeframes. And that's what matters in real deployments. If your agent takes 2 hours to analyze a cluster when you need answers in 45 minutes or 45 seconds, that model isn't useful to you, no matter how good its eventual output might be. But some models had truly disastrous reliability issues that go beyond just being slow. GPT-5 Pro was the real shocker here. This model couldn't complete nearly half of all evaluations, only 52% participation rate. It exceeded timeout so often that it failed more tests than it passed. Pattern recognition? 0. Couldn't finish within the time budget. Recommendations? Also 0. Nothing. GPT-5 Pro is supposed to be the advanced version of GPT-5. It is positioned as the model for complex reasoning tasks. And here's the thing. These aren't impossibly hard tasks. We are talking about Kubernetes operations that production agents need to handle. It's like having a brilliant mathematician who might excel at complicated algebra, but takes hours to answer, hey, what's 2 plus 2? Being brilliant doesn't mean much if you cannot answer straightforward questions relatively quickly. Then there's Mistral Large. Now, I expected Mistral might struggle. I did. It's generally not considered among the absolute top-tier models. I included it anyway because, hell, we need to support European AI development as well, right? But the results were rough. This model couldn't finish remediation investigations at all. 0 score. It would start the investigation loop but couldn't complete the systematic troubleshooting process within the time constraints. Only 65% participation rate overall, meaning it failed to complete a third of all evaluations. Now, let's talk about cost, because this is where things get interesting. The cheapest model isn't always the best value, and the most expensive definitely isn't either. For example, Grok 4 Fast Reasoning absolutely dominates the cost-performance category. It accomplished a value score more than 3.5 times better than the next competitor. At 35 cents per million tokens, that's 20 cents for input and 50 cents for output, is the cheapest model in this evaluation. But here's the catch. Remember that policy compliance test I mentioned earlier? Grok 4 Fast Reasoning couldn't complete it within the 15 minutes window. It scored around 40%, which is catastrophically low. This makes it production dangerous for policy generation workflows. So, yeah, it's cheap and fast for most tasks, but you absolutely cannot use it for generating, let's say, kernel policies. On the other hand, Gemini 2.5 Flash offers a more balanced value proposition. At 30 cents for input and $2.50 for output per million tokens, it delivers solid 78% overall performance with no critical failures. It's about twice as cheap as some premium options while still being production ready across all scenarios. Now, about those premium models, some of them cost anywhere from 8 to 20 times more than budget options. The question is, do they deliver proportional value? We'll see that one later. And then there's GPT-5 Pro. Remember that model that couldn't complete half of its evaluations? The one with 0 scores in pattern recognition and recommendations? That one costs almost $68 per million tokens. $15 for input and $120 for output. It's so ridiculously expensive compared to everything else that it actually screwed up my cost versus quality graph that you see on the screen. Now, looking at tool-specific performance reveals something interesting. There is no universal winner that dominates everything. Instead, we see specialization. Some models excel at certain tasks but struggle with others. In capability analysis, the performance spread is massive, from 90% at the top down to around 64% at the bottom. There's a significant difference in how well models handle these 100 consecutive interactions over 45 minutes. Pattern recognition shows even more dramatic variance. Some models excel at this rapid 5-minute workflow, while others, remember GPT-5 Pro? Scored absolute 0. Couldn't complete it at all. They're not even in this graph. Policy compliance ranges from 83% down to 40%. That bottom score is Grok 4 5 Reasoning, failing to complete the comprehensive schema analysis within 15 minutes. For recommendations, we saw a 42 times speed difference between the fastest and slowest models. Same task, same schemas, widely different completion times. Some models process those 100,000 plus tokens efficiently, others choke on them. And remediation shows the widest gap of all. Complete failures at 0 versus near perfect scores at 95%. This systematic investigation workflow really separates the capable models from the ones that just cannot handle iterative problem solving. And here's where things get really interesting. Context window size matters, but efficiency matters even more. The pattern is clear. Models with larger context windows generally score higher in recommendations. Makes sense, right? That scenario sends 100,000 or more tokens of context in each interaction, including up to 50 large Kubernetes schemas. Bigger window means more room to work, right? Well, not really. Look at Claude Haiku that completely breaks the pattern. This model has only 200,000 context window, yet it scored 93%, the highest score in the entire recommendation category. It's processing these massive context loads with 50 plus schemas more effectively than models with 5 times larger windows. That's not about having more space. That's about using the space you have more efficiently. Now, on the flip side, Grok 4 fast reasoning has a massive 2 million token context window, but could not complete tasks within the timeout constraints. All that capacity, but it cannot process the information fast enough to actually matter. The lesson here is clear. Context size alone doesn't guarantee performance. It's about how efficiently the model utilizes what it has. Now, when I synthesize all this data, the reliability issues, cost trade-offs, tool-specific performance, and context efficiency, clear performance tiers emerged. 3 distinct categories separated by real performance gaps. Let's start at the bottom. The bottom tier includes models scoring below 70% overall or below 80% reliability. 4 models landed there. Now, 2 of these are expected to struggle. Mistral Large and DeepSeek Reasoner aren't generally considered top-tier models, so their results were not surprising. DeepSeek struggled with pattern recognition and endurance testing, while Mistral couldn't complete remediation investigations. Not great, but not shocking either. Now, the real disappointments were GPT-5 Pro and Grok 4 5 reasoning. These were supposed to be competitive options, but they failed in ways I didn't anticipate. The primary issue? They take unreasonably long to analyze tasks, consistently hitting my timeout constraints. GPT-5 Pro could not complete nearly half of all evaluations. That catastrophic 52% participation rate, with 0 scores in pattern recognition and recommendations. It's not that it got the answers wrong. It's that it could not deliver answers within specific timeframes. And Grok 4 fast reasoning, with fast literally in its name, has that production dangerous 40% policy compliance score because it could not, and I repeat, could not complete the comprehensive scheme analysis within 15 minutes. The irony of calling it fast when it consistently exceeded timeouts is kind of funny. It's not lost on me. The bottom line, these models have critical failures that make them unsuitable for production use. Or at minimum, you would need to be very, very careful about which scenarios you use them for. Now, moving up to the mid-tier, we have 4 models that are actually production ready. They score between 70 and 80% overall, with at least 80% reliability. This includes Gemini 2.5 Flash, our balanced value champion at 50 cents input and 250 output per million tokens. GPT-5 without Pro, with its solid consistency in pattern recognition. Gemini 2.5 Pro with strong capability analysis despite that weak remediation score, and Grok 4 with good reliability and remediation performance. These are dependable models with some tool-specific weaknesses, but nothing catastrophic. They will get the job done, just not at the absolute highest level. And then we have the top tier. What's interesting is that the data naturally separated into those groups. There's a real performance gap between the mid-tier models clustering around 75-80% and the top performance. The top-tier models consistently score above 85% overall, with significantly higher reliability and consistency scores. They're not just a little better, they're noticeably better across the board. Only 2 models made it here. Claude Haiku, which was released in mid-October, very recently, scored 87% overall. Actually, the highest overall score in the entire evaluation. It leads in 4 out of 5 tool categories: capability analysis, pattern recognition, recommendations, and remediations. This is the model with only 200,000 context window that somehow achieved the highest recommendation score, 93%. Its efficiency is remarkable, and it costs $1 input and $5 for outputs per million tokens. Claude Sonnet also scored 87% overall, slightly lower raw performance than Haiku, but it has the highest reliability and consistency scores in this entire comparison. 98% reliability and 97% consistency. It achieved 100% participation rate across all evaluations, never failed to complete a test, never exceeded timeouts. When you absolutely need your agent to finish what it started, this is your model. But that reliability comes at a premium. $3 input and $15 output per million tokens. That's 3 times more expensive than Haiku. So here's the trade-off between these 2 top performers. Haiku gives you the best raw performance across most scenarios at a reasonable price, but with around 90% reliability. Sonnet gives you near perfect, 98%. It will never fail you, but at 3 times the cost and with slightly lower performance in most categories. Both are excellent choices. The question is whether you're optimizing for maximum performance or maximum reliability. Okay, now I've shown you the data, the failures, the costs, the performance patterns, the tiers. But data alone doesn't help you make decisions. You need concrete recommendations. Which model should you actually use? Let's break this down from worst to best so you know exactly what to avoid and what to adopt. Now, before we dive into the rankings, the final summary, there is an important note. This ranking is specific to Ops, DevOps, SRE, and software engineering tasks. Models that scored low here might excel at other types of work like creative writing, general conversation, or completely different domains. Similarly, models that scored high here might not be the best choice for everything. This comparison is focused on agent-based technical workflows. Keep that in mind as we go through the rankings. 10th place, GPT-5 Pro. $15 per million input tokens, $120 per million output tokens. You want me to pay premium prices for a model that cannot finish half the tests? This thing failed more evaluations than it completed. When it does manage somehow to finish something, it takes forever. You want us to pay those prices for this? Hell no. Now, 9th place, Mistral Large. This is marketed as Europe's answer to OpenAI, Europe's shot at AI independence. It cannot even troubleshoot a Kubernetes cluster. Zero in remediation. Failed a third of all tests. Come on, Europe. This is embarrassing. 8th place, DeepSeek Reasoner. The model everyone's talking about. Trained for pocket change. OpenAI thinks they stole their data. Great benchmark scores, and it cannot handle real agent workflows. Below 70% overall. Turns out you can game benchmarks, but you cannot fake production performance. 7th place, Grok for Fast Reasoning. Oh, fast reasoning? Except it's neither fast nor good at reasoning. Exceeded timeouts on complex analysis, 40% on tasks requiring systematic thinking. What's the point of putting reasoning in your name if you cannot reason? cheapest model, that's true, at 20 cents input, 50 cents output. You get what you pay for, I guess. These were the models you should avoid. Now let's look at the middle of the pack. Models that actually work but will not blow your mind. 6th place, Gemini 2.5 Pro. Mid-tier performance. Nothing exciting, nothing terrible. The model you choose when you have no strong opinion. It works fine, it will not impress anyone. Then at the 5th place, Grok 4. Mid-tier, reliable, boring. It will not blow your mind, but it will also not let you down. It's Elon's safe option. Then, on the 4th place, GPT-5. Without Pro. The normal version, not the expensive disaster. Mid-tier, consistent, predictable. It's like Toyota Camry of AI models. Gets the job done without drama. And now we're getting to the good stuff, the top 3. Models that actually deliver. In the 3rd place, Gemini 2.5 Flash. It's the best value for money. 30 cents input, $2.5 output, 78 overall performance with no catastrophic failures. When your CFO asks why you're spending money on AI, show them this model. Good performance, reasonable price, smart choice. Then, on the 2nd place, Claude Sonnet. $3 input, $15 output, 87 overall, 98 reliability. The highest in this entire comparison. It never failed a single test. When you absolutely cannot afford your agent to crop out, this is your model. Enterprise-grade reliability. 3 times more expensive than Haiku. Worth it if failures cost you money. And now, the winner. 1st place, Claude Haiku. $1 input, $5 output, 87% overall. Tied with Sonnet but wins on raw performance. Leads in 4 out of 5 categories. And here's the kicker. Only 200,000 context window, yet it achieved the highest score for processing massive context loads. That's not about having more space. That's about using what you have efficiently. Best price performance ratio. This is the model to beat. Use this. Use it unless you're not price conscious and you can afford Sonnet's premium for maximum reliability. So here's the bottom line. Start with Claude Haiku for most work. Switch to Claude Sonnet when you need that 98% reliability and you can afford the premium. Use Gemini 2.5 Flash when budget matters. And avoid the bottom tier entirely unless you have very, very specific use cases where their weaknesses do not matter. So here's the question. Was this useful? Should they repeat those evaluations every time a new model is released? Which criteria do you think is missing? What should they include in future evaluations when new models appear? Let me know in the comments. The full report with all the detailed data is available at the address over there. Thank you for watching. Hey, it's in the description as well. Thank you for watching. See you in the next one. Cheers.